Yeah, for today, we're basically going to be doing the part 2 of the recurrent neural networks. And today we're going to be mostly focusing on the LSTMs that were in the readings in the video that we kind of sent around. And like last time, we have some learning outcomes that we want to meet. But again, I won't go through them all in detail right now, but we'll kind of revisit these learning outcomes as we go. So as a quick review of recurrent neural networks that we were looking at last time, the data that we were working with consisted of a sample that was made up of multiple, that was a time series, and that time series was made up of multiple data points. So in each time step within the time series, there was one data point that we were looking at. And we were looking at that example of kind of a sentence structure where each time step is one word in the sentence. And then on the left, we see our recurrent neural network structure. And we see that it's like a lot of the other neural network structures we've been looking at, but the special piece is that recurrent connection that kind of goes back from the top hidden layer back to the first hidden layer. And the idea behind this was that for each time step, that data point that's being inputted can kind of affect the next time step as that kind of information is passed forward. We also looked at this unfolded representation where we kind of can look at all the time steps at once, and then those recurrent connections. Let me just pull up my little laser pointer here. So those recurrent connections appear as arrows that kind of cross these time step boundaries. And then we saw that we could have, a single output at the very end of our sentence, let's say. So if we would put in those words there, we could kind of have the data from each time point flow through this entire network and give us a single output if we wanted to classify that sentence, let's say. But then we did a whole bunch of math, and we saw that for very large inputs, so if it's a very long sentence, let's say, this RNN effectively becomes very deep. And then if we want to try to train it using, backpropagation and using the gradient descent techniques, we end up with a vanishing gradient problem that causes the RNN to kind of forget the beginning of the sentence, but for it to mostly incorporate the end of the sentence that's nearest the output, which is not really what we would want. So today we're going to be learning about basically how we can counter this. So I'm going to use a bit of a different example today. So instead of using this sentence input that we were looking at before, instead we're going to look at an example that is an EMG example. So this idea is basically we have electrodes on somebody's arm, let's say, and we can read. Here we have a 2-channel setup, so we have 2 voltages that are being recorded by a computer. This is an example graph that we could have of those 2 channels. So over time, the voltages of those electrodes change. And maybe we want to use these signals to try to classify what that hand is doing. So maybe it's grasping things in different ways. And you can imagine for like different wearable technologies, this kind of machine learning technique would be really useful to do. So for our recurrent neural network, that input is now going to change so that that first hidden layer is going to take 2 scalar inputs in for each time step. So those are the data at each channel. And then it also is going to take that recurrent connection in as input. So just to drive it home, at time step equals 0, we kind of have a single scalar in light blue, single scalar in dark blue. That corresponds to these 2 data points. So that's just a single voltage value. And similarly, we could go to the next time step, and it would be different values that would be going into these 2 channels. So that's our setup, but now we want to really fix this vanishing gradient problem. So what we're going to end up trying to do is to build what's known as a long short-term memory network. And again, this is a review that from slides that we saw last week. So again, we have this idea that all neural networks have really excellent long-term memory. And that long-term memory is the idea that the samples that you show the network during training, it remembers in the weights and biases, the parameters of the network. And because those parameters can be, saved on the computer on a hard drive, they're not going to go anywhere. So effectively, the network is remembering very well long term. But conventional neural networks have no short-term memory. So if we show it one sample and then show it the next sample, it's forgotten the last sample, which again, that's not the behavior that we want in our neural networks when we are working with these time series. So then, as we said, recurrent neural networks are designed to have this short-term memory, but the vanishing gradient problem makes them have short-term memory. So they only remember, the last few words in the sentence when they're trained. Not what we want. So what we want is to have long short-term memory. And this is going to be achieved using what are known as long short-term memory cells, or LSTM cells. And we'll see how these LSTM cells are designed to basically explicitly have this idea of long short-term memory. So this already allows us to check off kind of the first piece of our learning outcomes, and this is to just know what LSTM means. And as we know, it stands for long short-term memory. So I'll just be using that acronym moving forward. So at a very high conceptual level, we can kind of imagine our LSTM cell as a sort of kind of box, or some kind of computer that's going to do some kind of calculation. And what it's going to do is it's going to take some inputs, and that's going to kind of be fed into it. And within the cell is going to be some kind of memory blocks. And here, each of these shapes is kind of representing a single scalar value. So for our inputs, 2 blue squares means that it's a vector of 2 elements that's being put as input. And these diamonds, which are going to kind of represent just values that are moving around our LSTM cell and network, each of these is also representing a single scalar. So our memory in this case has 3 scalar values that it can kind of store. So what we want is for our inputs to basically affect our memory. So I'll show a changing value within these elements as a changing color. So we can see kind of our pink diamonds here, and then those values change, and now they're kind of a lighter pink. So that pink will represent memory, whereas different shades of pink will kind of show those memory values changing. And then we also want our LSTM cell at this point where we have inputs and memory, we want it to then produce an output. And that output is going to be kind of take values from the memory, kind of combine them with values from the input, and then that's going to give us some outputs. And let's say our output, we're going to represent it with orange, has 3 scalar values as well that we'd want it to have. And if we keep this idea of kind of a recurrent neural network going where we have multiple time steps, we would imagine that we would have inputs at the next time point. And if we want this LSTM cell to operate in a very recurrent nature, what we would do is we would take these outputs and kind of feed them in as input at the next time step. So kind of that recurrent connection. So it's not shown explicitly here, but we're kind of just taking these output diamonds, bringing them in as input diamonds. So then what we can imagine is taking these kind of 5 scalar values as input. So these 2 explicit input values from our time series, as well as the output from the last time step, those are fed in. And we could have those adjust the memory, and all of that could be fed together to get our output for our next time step. So at a very high level, that's what our LSTM cells are going to do. And now what we're going to go into is a more in-depth kind of look to see how that could actually be done using mathematical operations. So we're going to start off with, again, our memory. So I've just taken those 3 diamonds and I put them vertical because it's going to work better for this diagram. So that's our memory. Mathematically, we're going to represent that as C sub t. So that's cell, which gives us the C, and then the underscore t is for whatever time step we're at. So this is the memory at time step t. Again, similar to our recurrent neural networks, we're going to have time flowing from left to right. So at at the end of our kind of time, we're going to have, again, these memory values, and they're going to be at the next time step. So C sub t plus 1. So time step plus 1. And as we said, these memory values should change as that time step occurs. So this is how they're going to have lighter values. So they're still pink, so they're memory, but they're going to be lighter, so they're going to change values. And then we are going to draw some arrows to kind of just show kind of the values going across time. So we have our memory values, the single scalar value goes across time to here. And we're going to kind of show operations occurring along this line, as we'll soon see, that kind of allow the value to change. Whereas usually if two shapes are kind of just joined up by an arrow, that means that that value is just kind of flowing around the LSTM cell, but not changing values. So on the lower left, we're going to have our inputs coming in. So again, two scalar values. You know, going back to our EMG example, those two channels, let's say, that are being inputted. And we're going to represent that with x sub t. So the input at time step t. And then we are also going to have our hidden layer, which we'll see is kind of also the same as the output of our network. And again, this is three scalar values, and we're going to represent that with h sub 0 comma t. So we could have multiple hidden layers, as we'll see at the very end of this lecture. And then the t is, again, just representing time step t. And similarly to our memory, we could have our hidden layer have different values at the end of the time step. So at time step t plus 1, we will have a different shade of orange, which is representing those hidden layer values changing. So similarly to our memory, we'll kind of plumb those up with some arrows. And right now, those arrows aren't really changing the values, but as time goes on, we'll see how we can actually change those values. So we kind of have this general structure set up for our LSTM cell. And this very much mirrors what we saw in our high-level schematic. So we have inputs, and we have our hidden layer coming in. It interacts with the memory, and we'll see how that interaction plays out shortly. And then we have our final output. So when we're wanting our memory values to change from time step t to time step t plus 1, we are going to kind of look at different ways that we can change that memory. So the first idea we're going to do is we want the memory to be able to forget unneeded information. So let's say the memory kind of got some value somehow at the first time step, but 10 time steps later, that's no longer relevant for it to know. We want this LSTM cell to somehow be able to kind of forget certain values within the memory. So the way that we'll do this mathematically is to multiply each one of these scalar values, so each one of these diamonds, whatever value it has, multiply it between a value between 0 and 1, where 0 is going to represent forgetting, 1 is going to represent remembering. And these LSTM cells are going to be kind of special because if we multiply by a value 0.45, that's going to kind of be a semi-forgetting, semi-remembering state. And that's going to be allowable within our LSTM network. So it doesn't need to be just a binary forget, remember. So we'll use an example to just show how this works. So let's say within this first diamond, it has the value -4 at the beginning of the time step, 7 in the second value, 2 in the third. Then we can imagine we can multiply these values, the first one by 0 to forget, the second one by 1 to remember, and this third one by some value in between, kind of, again, that in-between state of remember and forgetting. And then this will give us some, a final value for each position in this memory. So we can see that arithmetic plays out as we'd expect. And this now represents the new state of the memory. So that's kind of represented by these diamonds that are now a different shade because they've changed color. So now we're going to represent this more diagrammatically. So we're going to represent what we just did using this. So basically these multiplication symbols that are kind of white on black are going to represent a value coming in, so 0 coming along that arrow, -4 coming along this other arrow, and we're just going to do an element-wise multiplication. So there's nothing crazy going on where it's like a matrix multiplication or anything. It's basically just saying multiply. And then the answer kind of comes out this other side where the arrow is exiting, so we can see 0. So easy enough to do, just a different way of representing what we did before. Now the question is, we can imagine we have some memory values coming in, some memory values that they're going to get changed to, but where do we kind of decide where that 0 or 1 or whatever value is going to be multiplied by to forget or remember? Where does that value come from? So what we can do is we can take these hidden layer and input values and kind of make a copy of them that are kind of just sitting here ready to be used. And we could somehow inform the values that should go into these question marks to be multiplied to either remember or forget. And, because we're working with neural networks, the best way to do that is to just plumb in a little neural network like this. So what this is basically a fully connected neural network where we have the value for each one of these element-wise multiplications is the output of a neuron. And each of these neurons is fully connected to each one of the inputs. So where those inputs are some from our time step inputs, x sub t, and some of those inputs are the hidden layer values. And again, those are just being copied by these arrows effectively and bringing them to this tiny neural network. Now, as we've said, we want to multiply by values between 0 and 1. And that will help us decide what kind of activation function should be within these neurons. So as we know, the sigmoid function represented by the symbol sigma does exactly that. So whatever input we give it, it'll give us a value between 0 and 1. So that's a good activation for us to choose. And we'll represent that by just putting a sigma within our little neurons there to represent the activation function that's in there. So this is what's known as the forget gate within our LSTM network. And the reason for that is basically this kind of little neural network is giving us values between 0 and 1 that are kind of controlling or are kind of a gate to whether values within our memory are going to be forgotten or remembered. And how this forget gate performs can be determined by the parameters of the neural network. So there would be a vector of biases. So there would be 3 bias values that we could tune here, as well as there'd be a matrix of weight values. So 3 times 5 or 15 weight values that can be individually tuned through the training process. So we'll represent these each with a different letter, and then the subscript F for forget. So if we kind of strip all that away, we can see that we kind of have the beginnings of our LSTM cells. So we kind of did some data plumbing, put in a little neural network here, did some multiplications, and now our memory can now forget values. So good first step. But we also want our memory to be able to remember things. So if we're constantly basically losing values, nothing's going to be ever inputted into our memory. So it's not a very useful memory if we can't do that. So the way that we're going to have our memory basically remember things is to add values between -1 and 1. So we're going to take our values that came out of our forget gates, and we're going to represent this kind of the memory remembering things by doing these operations, adding 0.3, subtracting 0.8, adding 0.1. So this is kind of being values that are being added to the memory. And then the final calculation could be, some values here. And we can see here that, the color of our memory has changed again because the values have changed. So we had memory values coming in, the forget operations happened, the values changed, then this remembering functionality occurred, and then the values changed again. So again, we can represent this more easily in our diagram by using these plus symbols with the white on black. And again, that's just showing, the values that come in are being added together, and then the output is where the arrow's leaving from those little elements. And similarly to our forget gate, the question is, how do we get these values? And as you might imagine, we make another little neural network. So we take those same hidden layer and time step input values and kind of line them all up, join them up with some neurons in a fully connected network, and then those outputs are going to be the value that gets added into our memory. Now we want values being added that are between -1 and 1. So again, that informs our activation function choice. If we look at the hyperbolic tangent function, or tanh, we can see it has that exact behavior we want. So for any input from negative infinity to infinity, our values will always be between -1 and 1. So we'll represent this with the letter T, and we'll pop it into our activation functions to basically demonstrate that those neurons have a different activation function than the sigmas within our forget gate. So this gives us a second neural network within our LSTM cell, and we're going to label this the candidate memory. So this is basically memory values that are basically can be added into our memory slots here. And again, this little neural network can be tuned through training, and it would have different parameters than that forget gate. So it would have different bias vectors, subscript M here, different weight values, again, subscript M. So we can tune it differently to our forget gate, which would be useful. We don't want it to behave exactly the same as our forget gate. So this kind of is the second step of our LSTM network completed. So we basically have the ability to forget and the ability to kind of have values added into our memory. But we also want to control or gate how much of this candidate memory, so the values coming out of these neurons, how much of that we want to add. So we can kind of turn on the faucet of how much to add to our memory as we want, to add some fine-tuned control. So we can control this very similarly to our forget gate by multiplying between values 0 to 1. So again, if we had our candidate memory values that we were using before, we can imagine we can multiply them by some value between 0 and 1 that basically controls if they get added into the memory or not. So this gate multiplying by 0 kind of says, oh, that's great that this value of -0.8 wanted to be added into memory, but this gate is going to say, nope, not going to add it in, where this value of multiplying by 1 allows it to be added. And again, we could have a value between 0 and 1 that allows us to add some of the value into our memory. So running that calculation through, again, that's just the multiplication occurring, then the addition occurs, and those are the values that'll get put into our memory values. So again, we'll represent this a little bit more diagrammatically using these white on black multiplication symbols, where again, that's just the values coming in, multiplied by each other, gives us the output. And similarly, we need to find some values to basically control these multiplication gates, and we use another little neural network here. And we again want values between 0 and 1, very similarly to our forget gate. So we just use this exact same activation function and plop that sigmoid activation function into this neural network. So this is what's known as our input gate. And that's basically just because it is gating or controlling the memory that gets inputted into our memory. And again, it can be individually tuned because it's a different neural network than these other two. So it would have its own biases, its own weights with subscript I here. And basically what occurs here is that this candidate memory network and this input gate network basically work together to add to the memory. So the candidate memory network kind of generates those values to be added, where the input gate kind of controls whether they're added or not. So it's kind of a two-step process to add something into our LSTM network. So we can just strip that away a bit, and we can see that our LSTM network is really starting to take shape here. So it's maybe looking a little bit more complex than when we started, but we've kind of gone through it and we know what each piece of this LSTM cell is doing. We have the ability to forget and the ability to remember so far. But if we analyze our memory so far, we can see all the arrows are kind of running into it as input. So values are kind of coming from these networks and coming into our memory through these purple arrows. But at no point are there arrows pointing the other way around. Values from the memory are never kind of coming into our network. And in particular, that's a problem because our hidden layer here is going to be our output at the very end of our network. And if this hidden layer never gets data from our memory, there's no real point of even having that memory. We're never using it. So some way we need to be able to get values from our memory into our hidden layer. And as we can see here, if we kind of follow an arrow through from our hidden layer at the beginning of the time step, we can run that all the way through, and we can see that that value hasn't even changed yet. So basically, if we would run this right now, those orange diamonds would stay the same shade. They wouldn't change values, which is not what we want. We want that hidden layer value to change over time. So the way that we can do this is to try to figure out some way to basically join the memory up to that hidden layer value at the end of our time step. So what we'll do is we'll kind of disconnect it from our hidden layer that came in to the network. And instead, we'll just, maybe we'll just plumb some values from our memory and just say, you know what, this first memory value, that'll just become our hidden layer output first value. And similarly for the second, similarly for the third. So that's definitely, one way that we can do it. And it's important to note that this operation of kind of taking the value out and passing it to the output doesn't change the value of the memory. So we can see dark pink, dark pink. Taking this value didn't change the memory at all. It didn't reset it, let's say. So for our hidden layer output, we want these values to be between -1 and 1. And we could see that, because there's this addition operation coming in, these values within our memory might not necessarily be within that range. They might be less than 1, they might be greater than 1, very possible. So again, we can use our hyperbolic tangent to help us with this. So we're going to add in these little white on black t's, which are going to just represent applying the hyperbolic tangent value to the scalar value. So a scalar value comes in, hyperbolic tangent is applied, and then that output is carried on to the hidden layer. So it's important to note that these are not neurons. So this white on black t is different than this black on white t. So this black on white t is doing, the inputs multiplied by the weights, adding them all together with the bias, and then applying an activation function of hyperbolic tangent. Whereas these white on black t's that's coming out from our memory is basically we just take some value b, do the hyperbolic tangent, and then some output value a comes. So there's no weights, biases, anything like that. So right now we can see that we have some values coming out of our memory, which is great, but the disadvantage we have is that right now, basically, whatever our memory is, that's what our next hidden layer is. And that means that these values in dark pink are going to be the same values as these light orange values, which is not a huge problem, but it's a little bit redundant. So when we're passing these values on to the next time step, we're kind of losing some flexibility in our LSTM cell to pass on different values. So what we'll do instead is basically control, or again, gate the use of these memory values as our output for our hidden layer by multiplying by values between 0 and 1. So again, we can represent that with these white on black multiplications. So we're basically going to have that output of the hyperbolic tangent, and we're going to say, do I want to multiply by 0 and don't use that value, or do I want to multiply by 1 and use that value, or do I want to use 0.3 of that hyperbolic tangent value to inform my hidden layer output? So again, we would wonder, how do we come up with these values for our gates? And we would use, again, a little neural network that uses our hidden layer values that come in at the beginning of the time step, our time step input values, does a fully connected network, and again, we have the outputs of the neurons controlling these multiplication gates. And again, because we want values between 0 and 1, we use the sigmoid activation function. So stripping that away, we can see our LSTM cell is basically complete at this point, where now we have our hidden layer values at the end of the time step being informed by the memory, but also controlled by the current hidden layer values and the input that we have. So this little neural network that we have is called an output gate, because again, it's gating what is basically outputted from the LSTM cell. And again, this can be individually tuned to operate differently than the other gates. So it have its own set of biases and weights, again, subscript O for output. So we can see in total in our LSTM cell, we have 4 kind of tiny neural networks: the forget gate, input gate, candidate memory, and the output gate, where all the gates have these sigmoid activation functions to get their values between 0 and 1. And again, all of these networks are individually tuned. So they have their own biases and their own weights that can be decided upon. So what we can do now with this very complex diagram that we have is we can basically start to simplify it. And as we simplify it, we'll see that it kind of takes a shape that might be more commonly found in the articles and papers that we see online. So the first step we'll take is to take this tiny neural network here and we'll condense it into a single block. So we'll represent it like that. So we have, again, our inputs coming in, and we have 3 outputs. And we represent our activation function with our sigma here, where this intended meaning is to basically mean we have 5 inputs and we have 3 neurons that are producing our outputs. So we can do that for the rest of our neural networks that we have here. And we can see that they become sigma, hyperbolic tangent, and sigma. And then what we can also do is right now we're kind of showing the flow of scalar values through our LSTM cell. But of course, you know, this hidden layer could be 10-dimensional with 10 scalar values being passed around. And representing it in this style would quickly become cumbersome. So what we can do is we can kind of condense these 3 scalar values into a single thick line. So we'll see that that kind of occurs like this. So we can see our dimensionality of our hidden layer here. So 3 values, but they're kind of being passed along as a vector to each of our little neural networks. And we'll do the same for our input. So we can see it's being passed around as a vector, and it has those 2 scalar values. Now what we are going to do is we're going to do the same to our memory. So we can again represent that memory more as a vector. And we're going to take our multiplications and represent that as a vector as well. So those 3 outputs that we had from our input gate for those 3 neurons that were in there kind of are condensed onto one line now. And then they're passed to this multiplication kind of as a vector. And then element-wise multiplication would occur, and that would kind of produce the same operation that we've been showing so far. So we'll show that element-wise multiplication as kind of this rounded square with the multiplication in it. So we can see we have 3 values being passed in from the memory. We would have 3 values being passed in from the input gate. The first element of each would be multiplied. The second element of each would be multiplied. The third element of each would be multiplied. And then that gives us a vector on the way out, which, as we can see here, still has 3 values within it. So we can apply the similar operation to our input gate and our candidate memory. Again, vectors coming in, element-wise multiplication. And again, they're flowing out to those additions, which again, we can represent more simply using these thicker lines for the vectors, and then this addition block to show element-wise addition. And lastly, we can do the same for the rest of our memory. So again, vector values for our memory, it gets each element of that vector of memory gets passed out towards the output gate. And again, we could represent this with an element-wise hyperbolic tangent, element-wise multiplication, element-wise input from our output gate network. And then finally, we have our hidden layer output that also becomes vector valued. So we can see here this kind of really simplified our diagram and kind of allows us to see the big pieces. Again, each of these gates and candidate memory and these element-wise operations that kind of allow us to interact with the memory, both giving value, forgetting values, inputting values, and then taking values out of it. So what we'll do at this point is we'll kind of just draw a big line around this, and this kind of encapsulates this into what's known as an LSTM cell. And we'll kind of zoom out on it, and we can see that, you know, we still have all that same representation that we had before with all these gates and different element-wise operations. But now it's kind of packaged up into a nice little piece that we can start to join together as we'll see over different time steps. And as I said, this is known as a memory cell, kind of, you know, because it's kind of a compartmentalized piece with all these other little subcomponents inside of it. And often it's called just an LSTM cell or simply a cell. So jumping back to our learning outcomes, realized that was probably a bit of a doozy of an explanation, and we were going through a lot, but we kind of knocked off 3 of our learning outcomes by doing that. So first, we learned to fill in the correct element-wise operations on an LSTM schematic, so we know where those multiplications, additions, hyperbolic tangents go. We know where the forget gate, input gate, candidate memory, and the output gate are within the LSTM cell. And also, because we kind of worked through that example, if we were given the input values for the LSTM cell, like the memory values, the hidden layer values, and the time step inputs, we'd be able to compute the output of it if we were given all the weights, biases, and all that. But, you know, in practice, these LSTM cells are very multidimensional, and so doing that by hand would take a long time. So it's quickly done by computations. So if we jump back to our LSTM cell now, we can see that we have, again, our inputs, or our inputs for our hidden layer, inputs for our time step, and our memory cells. And I'm putting the mathematical notation back on here so that we can just take some time to notice the time indexing. So we can see these pink diamonds here are for the time step t, these orange ones here for the hidden layer, time step t, and again, the blue squares, inputs at time step t. Whereas on the right side of our cell, we can see that these values are representing the values for time step t plus 1 in both cases. So what this allows us to do is kind of draw those recurrent connections. Again, if we imagine this cell kind of being used over and over again at each time step, as we start up the next time step, the value that was at the right side of the LSTM cell kind of flows back and is fed back in as input. And again, similarly for the hidden layer, that kind of comes back. So those are our recurrent connections. So this would be the folded representation of an LSTM cell. Though typically we like to show this in the unfolded fashion to just be a little bit more clear about it. So let's do that by using a bit of an example. So again, we have our input data that we have. So it's a time series. So we have 3 time points, t equals 0, t equals 1, t equals 3. And we can see at each time step we have 2 values. So basically a 2-element scalar that we're having as input. So we have the 2 channels. So we can see at time step 0, we have 1 input, similarly for the other time steps. So at t equals 0, we would have our LSTM cell, and we would take these 2 values highlighted in yellow as the input. So again, 2 scalar values coming in. And we would have our hidden layer and our memory initialized to some value. Maybe it's random, maybe it's zeros, it could be whatever we want. So at this point, we can see that we don't know what our final hidden layer and memory values are for our LSTM cell. But because we have all our inputs kind of colored in here, we have the values, so we can just run this calculation through and we would get the values. And again, the colors would change because those values would change. So, you know, the memory changed values because it forgot and remembered some stuff, and the hidden layer values would change because it was informed by the memory. So then at the next time step, what we basically do is copy and paste our LSTM cell. And again, at the next time step, we can take the next data points in for input. So again, that would kind of fill in our blue squares there with 2 scalar values. And then for our hidden layer and our memory values, again, those are just basically copied from the output of the last time step. So those just get transferred over, same shade, same values. And then again, now that we have all our inputs ready to go, our memory, our hidden layer, and our inputs, we can feed it through that network, and then we get, you know, some new values at the end of that time step. Again, they're darker because they're different values. And then again, we can copy and paste our LSTM cell. We get the new inputs for time step equals 2, copy the values from the last time step. We have everything we need to calculate, run it through that LSTM cell, and then we get these values for the memory and the output. And then now, because we have finished all of our data points for our time step, we can now produce our output. And the way that we would do that is we would take our, you know, let's say our 3 hidden layer values at this point. There would be some fully connected network to a single neuron, and that would give us our output Y. And, you know, let's say that this was our EMG data and we were trying to classify, you know, between different types of grafts. We can imagine, you know, maybe it gives us a value 0.56, and that would be compared, if it was a training sample, to some known label. So let's say it was trying to be like a cylindrical grasp, like when you hold a glass of water, and that was given a label of 1. So again, similarly to what we saw last week, we can compare these two values, so the expected value of 1, or the target value of 1, to what it computed, and then this would give us some loss value, and that would help us train our network. And again, when we're training our network, we're training basically each of these little gates. So let's just focus on our forget gate. Again, that forget gate highlighted in yellow, if we kind of zoom in on it, we know that there's a bunch of biases and weights that we could possibly tune based upon this loss value that we have. And it's also important to note that because this is the unfolded representation, the biases and weights for the forget gate at each time step are the same. So that's shown by the same color yellow. So same bias weights at time step equals 2 as time step equals 1. So then what we can do to basically change these biases and weights to have this, you know, this output we calculated be closer to 1 is we basically back propagate using the gradient. So, you know, that would be shown, you know, through this purple line. We can back propagate till we get to, you know, the bias and weights here, the bias and weights here, and the bias and weights here. And basically what the advantage of using these LSTM cells is that these element-wise addition and multiplications basically work to basically break up those vanishing and exploding gradients. So instead of that, you know, that gradient value being multiplied to a very large exponent, these additions and multiplications kind of break that exponential behavior up and allows these cells to be trained more effectively. And what this basically allows is for the network to remember data from all the time points. So we could imagine that, let's say, in order to correctly classify this time series, we needed data from the first time step. The way that we can train this, we can basically have this input data kind of be added into the memory at this point. And if we tune our network correctly, we can make sure it's never forgotten, such that it gets all the way to our last output step and it informs our final output. So this is a great use of LSTM cells to kind of overcome that vanishing gradient problem. And again, we could draw an unfolded network for, let's say, a time series that was of a different size. So again, a big advantage of recurrent neural networks is that we can have input sequences of different lengths. So to show this, we'll kind of take our LSTM cell and we'll even crunch it down even smaller into this very condensed representation. And again, if we wanted to get the classification for this 5 time step time series, it would look something like this, where we have, again, our LSTM cell at t equals 0. We run that calculation through, gives us some values for our memory and hidden layer. Those are copied across, and we get our next input values, compute the memory and hidden values, and we keep on doing that all the way to the very end for our last time step. And then at that point, you know, we get our final output y based upon our hidden layer values. So this allows us to kind of cross off our 5th learning outcome. So this is basically to just understand how LSTM recurrent neural networks basically compute their values, and how when we compute the loss and want to basically train these neural networks, that the specialized memory operations, like those element-wise addition and multiplications, help us solve the vanishing and exploding gradient problem. So now we'll move on to some more complex LSTM networks. So far we've only looked at a single LSTM cell being used for each time step. So at time step equals 0, we had one LSTM cell. Next time step, we had that LSTM cell repeated. And the problem that we have with this is that we have limited dimensionality. So, you know, we had, you know, 3 scalars for our hidden layers, 3 scalar values for our memory, 2 scalars for our inputs. So it's a very low dimensionality network. And that, you know, we have some weights and biases to tune, but again, it'd be very few parameters. So we can make more parameters to increase the dimensionality to maybe help it fit a more complex relationship by just jacking up the dimensionality of our hidden layers and our memory values. So this is one way to do it. But another way that we can do it is similar to conventional neural networks where we have multiple layers. We could have, we could use multiple LSTM cells to make a multi-layer LSTM network. So this might be a bit hard to imagine right off the bat, but I'll show a bit of an unfolded example to demonstrate it. So again, going back to our time series where we had 5 time points, again, we would start off by having our LSTM cell at t = 0. And we have 2 input values that are going to be coming in. Then what we can do at the same time step is we can just have another LSTM cell. And it could have different dimensionality. So maybe its hidden layers only have 2 scalar values along with the memory. And it has 3 values coming in as input. And the way that we combine these 2 LSTM cells is the input of this second LSTM cell is going to basically be taken from the hidden layer of the first LSTM cell. So we'll plumb it up just like that. And if we kind of blow up these 2 LSTM cells, we can see their basic operations are the same. They have different dimensionality in their hidden layers and their memory, as well as their input. And these 2 the neural networks within the input gates and forget gates and output gates, candidate memory, can be tuned differently. So I'll show those as purple, so that's one set of weights and biases, and yellow, that's a different set of weights and biases. And we could propagate that coloring back just to differentiate these LSTM cells a little bit more clearly. So what this would give us is basically a 2-layer LSTM network. So we'd have layer 0 in purple, layer 1 in yellow. And basically, the output of one layer goes in as the input for the next layer. Very similarly to deep neural networks that we've seen before that aren't based upon a cell structure. And then for the next time step, very similarly to what we've seen before, the output values and memory values get put across to be the input for the memory and the hidden layer at the next time step. But the subtlety here is that we need to remember that in our layer 1, our second layer here, those hidden layer and memory values would also have to be brought across that time step. So there's recurring connections occurring at both layers. And again, the output of the hidden layer at this time step would become the input for the next time step, or to the input for the next layer, sorry. And then again, we would just keep repeating this for all the time steps. So we could see that the hidden layer and memory values at each layer are changing as time goes on, but the weights and biases stay constant across those time steps. But they can be different between the 2 layers, so the yellow versus the purple. And again, our output would now no longer come from our first layer, but would rather come from our second layer here, and that would give us our final output. So this gives us a bit of an idea of how we could draw a multi-layer LSTM network in its unfolded representation. And we could kind of see how the hidden layer and memory values could kind of flow through time. So we'll go one farther in our learning outcomes, and this will be useful when we start to do our Keras demo that Salma is going to lead us through. And this is to do multi-cell LSTM layers. So let's just break that down for a second. So again, we have LSTM layers. So we have the purple cell here is layer 0, yellow cell is layer 1. But we can see that at each time step, so if we kind of look at these orange borders, if we look at time step = 0, in layer 1, there's only a single cell. And in layer 0, there's only a single cell. So again, if we wanted to increase the complexity of our LSTM network, we could actually add multiple cells per layer. So let's again use our unfolded representation to break that down. So again, going back to our favorite example, 5 time step time series. Again, we would have our 2 input values to start off with. So those are, again, highlighted in yellow. So 2 scalar values coming in. Then what we can do is we can take 2 LSTM cells that have different hidden layer and memory values, shown with those different shades. And we could pass the input to both of them. So that basically, just very similarly to how we can have a neural network that has multiple neurons in the first hidden layer, the input values would be passed to all of those neurons. And if we kind of blow up those LSTM cells, what we could do is we could see that we could actually tune those, the forget gates or the input gates, output gates. We could tune those neural networks differently. So this is shown using different shades of purple. So they're both purple because they're both in that first layer, but they're different shades because they can be tuned differently. And because they're tuned differently, they're going to again have different output values. So maybe this hidden layer has some values, whereas the second cell's hidden layer will have some different values. So then we would have those values there, and we could kind of strip those away, and this would give us our layer 0. So it would be layer 0, and it has 2 cells per layer. Then what we can do is we could add on a second layer. And this second layer, again, we could have different dimensionality for our hidden layer, our memory, and our inputs. And again, we could have multiple cells. So here I have 3 cells. And then what we do is we take the hidden layer output from our first layer in the first cell, and we send that to be sent to the input of each of the cells at the next layer. And we similarly do that for our second cell, and we send that to the input for each cell at the next layer. And we can kind of imagine this being almost a concatenation. So half of the input comes from this cell, half of the input comes from this cell. And then for each of these LSTM cells at that next layer, we can kind of break those out. And again, these could all be tuned differently as well. So again, different shades of yellow means that they're tuned differently, but the yellow and the purple just differentiate the 2 layers that we're looking at. So again, breaking this down, we have layer 0, which has 2 cells in that layer, and layer 1, which has 3 cells, just like that. And then again, if we move on to our next time step, we could have new input values. So again, time step equals 0, time step equals 1, new input values. And then again, we just copy our LSTM cells over. So again, we'd have our first layer, and we'd have our inputs ready to go. And again, these would be tuned the same way. So same shade of purple for the LSTM cell, because those weights and biases for a single cell stay constant over time. And then again, we could take our next layer and again plumb up those outputs for the hidden layers to be the inputs for the next layer. And again, these LSTM cells would just be copied, so same biases and weights as the previous time step. So then what we'll do is we'll kind of just gray out the inputs being kind of traced through the network. And then we're going to look at the kind of the recurrent connections that need to occur. So that hidden layer value from our first cell in our first layer is passed on to the next time step to be the input for the hidden layer. And similarly, for our second cell in our first layer, that hidden layer value gets passed along through that recurrent connection. So the output becomes the input. And similarly for our memory. So again, each LSTM cell is kind of matched up with the same LSTM cell just in the next time step. And again, we can do that for our next layer, again, passing on those hidden layer outputs to become inputs. And similarly for our candidate memory, just like that. And lastly, we want our output. So again, that's going to be some final neuron Y. And the way that we plumb this up is we have hidden layer outputs from multiple cells now. And we just basically combine those all into one final fully connected network to give our final output value of Y. So this allows us to kind of draw off a bonus learning outcome where basically we can draw a multi-cell and multi-layer LSTM network. So that's kind of going beyond usually, what we would learn about. But because we'll be seeing that in our demo, I thought it was a good idea to include that.